Hola, hi, this is Al, your statistics instructor. Let's get to work. In this video, we will start our discussion about simple linear regression. To be more specific, we will find the least squares regression line by solving the normal equations. Let's begin. Okay, so before we start talking about simple linear regression and the normal equations, okay, we are going to need to remember a few things that you learned back in sta360 probability theory. Okay, these concepts will be useful because we are going to at some point we are going to obtain some estimators, and we would like to have alternative expressions for those estimators in terms of the quantities that we're going to discuss now. Okay, so first let me remind you about these definitions that I'm sure you saw in sta360. Okay, so first one is the definition of the variance of a random variable. So if x is a random variable with mean, let me use the notation mu sub x, and that only represents the expected value of the random variable x, then the variance, as you recall, is just an special expected value, right? It's the expected value of your random variable x minus its mean squared. Okay, so and I'm sure that you showed that there's an alternative formula to find the to find the variance of x, which is given by the expected value of x squared minus the expected value of x, the whole thing squared. Okay. So just just as we have the concept of the variance, and I'm sure that you saw that. I'm sure that you saw that back in sta360. I'm sure that you discussed the covariance between two random variables x and y. Okay, so another definition: if x and y are random variables with means mu sub x, and that guy again represents expected value of x, and we are going to have mu sub y, that guy represents the mean of y, right, the expected value, respectively. The covariance of x and y is given, as you can expect, by another expected value, right? And it is just an extension of the concept of variance. So what we're going to have here is the covariance between x and y. Instead of being the expected value of that x minus its mean squared, is going to be the expected value of this cross product. So it's going to be y minus its mean here, right? And then just as we have an alternative expression for the variance, we have an alternative expression for the covariance, right? And it's very similar to the one we have above. Okay. Now, from this alternative expression, what we know is that if x and y are independent, the expected value of x times y equals the expected value of x times the expected value of y. So if x and y are independent, the covariance is 0. So the covariance is a natural way of measuring dependence between x and y, right? The problem with that measure is that it depends on the units on which x and y are measured. So again, another one that I'm sure you saw back in probability theory is the correlation coefficient. Okay, so the correlation coefficient is basically just a standardized version of the covariance. Okay, we use the letter rho to refer to that guy, and is defined as follows. It's going to be just the covariance divided by the product of the standard deviations between x and y. Okay, so let me write it down here. Square root of the variance of x square root of the variance of y. Okay, or if you will, we could write it down like this, right? Covariance between x and y divided by sigma sub x times sigma sub y. Okay, just different notation that you could see out there. Okay, so just as we have the sample mean, which is a good estimator for the mean, right? We are going to have sample versions of these quantities. So for instance, for the variance, let's talk about the sample variance. The formula is going to be just summation of xi minus x bar squared divided by n minus 1, right? That would be our sample variance, or the estimator for the variance. Okay, so xi minus x bar squared divided by n minus 1. Okay, so the other one would be the covariance. Okay, and by the way, just as there are alternative formulas to find the variance and covariance of random variables, right? There are alternative formulas to find the sample variance and the sample covariance. So let me just write them down here because they could be useful. So here we are. I goes from 1 to n. We have xi squared and we're going to be dividing that guy by n minus 1, then minus, and then we have n divided by n minus 1 times x bar squared. Okay, x bar squared. Okay, So now what we're going to have for the sample covariance is going to be similar. So let me copy paste this. Sample covariance, right? We're going to be using the following notation for the sample covariance: S sub x y. Okay, as you can imagine, instead of having a square here, we are going to have a cross product and yeah, we're also going to have an alternative formula to compute this guy, right, the sample covariance. So there, instead of having a square, we're going to have a cross product, and here, instead of having just x bar squared, what we're going to have is x bar square, well, x bar times y bar, right? Instead of the square we had before, we will have this, right? X bar, y bar. Let me try to introduce there a space. That's better. Okay, so makes sense? So very similar to the definition that we had for the sample variance, right? Just an extension, just like for random variables, right? And as you can imagine, there's also a sample correlation coefficient, sample correlation, and that's given by R. We're going to be using R to denote the sample correlation coefficient, and it's going to be the sample covariance divided by the sample standard deviation of x times the sample standard deviation of y. Okay, so sample covariance divided by the product of sample standard deviations, similar to this, right? Okay, so let's just keep those in mind. They are going to be useful at some point. Okay, now let's talk about our main problem, right? We said that we were going to start our discussion about linear regression. So what's linear regression about? Simple linear regression. Simple linear regression. Okay. So what's the idea? The idea is that we have m pairs of points, right? So we have the following data. We have x1, we have y1, and then we have another pair of points, well, another pair of coordinates, because now points are represented by these pairs of numbers. So we have n observations, and now each observation is a pair, right? Now the first coordinate, the x coordinate, represents a value for a predictor variable, and the y coordinate represents what we call the response variable, the one that we want to predict. Okay, so we have n values for the predictor, n x's, and we have the corresponding y's. Okay, okay. So then we make a scatter plot. Okay, and then what we would like to do is to find the line that best summarizes that scatter plot, that best approximates, that best fits our data. Okay, so let me show you a graph. Give me just a sec. Okay, so here's the graph that I wanted you to see. Okay, so we have a scatter plot, right? We have in this case 5 points, and then we add a line, right? And maybe that that seems to be like a good summary of the relationship that we're seeing between these two variables, x and y, right? But then what we would like to do is, because we could propose another one, right? A different line. So how do we know that we have the best line? Okay, so the idea will be measuring the distance, the vertical distances between your predictions, your red line, and your blue dots. The blue dots represent your observations, the red line your prediction. Okay, so we're going to measure those vertical distances, we're going to square them, and we're going to add them up. Okay, give me a sec, I have another graph where I have those vertical distances. Okay, so see, these are the vertical distances I was talking about, right? So that would be the distance between observation and prediction. Observation, prediction. Observation, prediction. Observation, prediction. So we measure these, the lengths of these vertical lines, and we square them. And then for every line that we can think of, we just measure that quantity. And the winner is going to be the one that minimizes the squared of the sum of those vertical distances. That's going to be our criterion. Okay, so let's formalize what our criterion is going to be. Okay, so our criterion will be the following. Oh, give me just a sec. Okay, so as I was saying, right, our criterion will be the following. Criterion. So we said we are going to have a prediction, right? Let me call that prediction yi hat. Okay, so yi hat, and it's going to be an a plus a b times xi. Okay, so it's going to be a line, and this guy here is our prediction. Okay, now the model that we're assuming, right, the behavior that we believe our data has is something like this. The authors from our textbook, they use alpha 0 to refer to the y-intercept, plus beta, that's going to be our slope, our unknown slope, times xi plus epsilon, right? This is a random fluctuation for each of these observations. And the usual assumption is that those epsilons have a normal distribution. Okay, so we assume that those epsilons have a normal distribution with mean 0 and variance sigma squared. Okay, so we have a model for our observations. We know what our criterion, well, what our prediction is going to be, and the criterion is going to be this, right? We have our observations, right? going to measure the distance between our observations and our predictions. We're going to square it, and we're going to add up all those squared differences for every single observation. Okay, so here we go. So yi minus yi hat squared, right? And we do that for every single observation. Make sense? Okay. So this criterion has a special name. It's called the sum of squares for error, right? So if we write our criterion in terms of this, right? Let's do that. This is what our prediction looks like. Okay. So to find the best line, what we're going to be doing is minimizing with respect to A and B, right? That's what we're going to be doing. So we minimize that with respect to A and B. Okay? Make sense? Okay. So let me copy paste this. It's going to be better if we have it here. Okay? So if we think about this, right, what we're basically doing is, hey, we are proposing a bunch of different linear models, right, and we measure the distance between our candidates and the observations. We square those distances, and we are going to keep the one that has the smallest distance, right? So if we think about this as a function of A and B, what we have to do is very clear to solve the problem. What we have to do is take partial derivatives with respect to A and B, set them equal to 0, and then solve the resulting system. Okay? So, since we're going to need some room, let's do it somewhere else. But that's exactly what we're going to be doing. Okay. So let's find the partial derivative of SSE with respect to A first. Partial derivative of SSE with respect to A. So that's a derivative of a sum, so it's the same as the sum of derivatives, right? Let me copy paste this. It's going to be useful. So it's going to be 2 times this guy inside those square brackets, and then we use the chain rule and we take the derivative of what's inside those square brackets with respect to A, and that happens to be just -1. Okay, and then we're going to be setting that one equal to 0, right? Okay, that would be our first equation, right? Okay, now let's try and do the same for B. We have to take the partial derivative with respect to B of that function. So this could be useful. So let me copy paste, and then we're going to modify accordingly. So partial derivative of this with respect to B, so it's going to be 2 times what's inside those square brackets times the derivative with respect to B of what's inside those square brackets. That's going to be minus xi. You guys agree? Okay, so minus xi. And that's equal to 0. Okay. So that would be our second equation, right? So we are going to be solving that system, but before we do that, how about we try and simplify these equations a little bit more, okay? So let's play around with the first one. So this is the same as -2 times this, right? It's the same. These two equations are equivalent. But now this guy is a common factor. We can pull it out. So we have it there, right? And then we could divide by -2 on both sides, and we haven't done anything wrong, right? So this is our new equation 1, okay? Let's do something similar with the second equation. Let's try and simplify that a little bit. So in this case, we also have a -2 as a common factor, right? We could pull it out, that -2. We could divide both sides by -2, and that's an equivalent equation to the one that we had at first. Okay? Okay. Now, let's try and solve for A and B. Okay? Here we go. Let me expand this one. That's what we're going to be doing. So first we're going to have summation of yi's. Okay? No problem with that one. Then we're going to have minus n times a, right? So let me get rid of this one here. Summation of yi's, right? Minus summation of a's, right? That's going to be n minus n times a, right? So no problem there. Then we're going to have minus times plus minus b times xi. So we're going to have minus b times summation of xi's. Agreed? Oops. Let me do the summation here. Summation I equals 1 n, and then we have xi. Okay? That's an equivalent equation to 1. Okay? Now, if we divide by n, right, both sides, right, let's just say that, right, dividing by n, right, what we're going to have is y bar a, and we are going to have b times x bar. You guys agree? Okay, makes sense? So, well, we could solve for a, okay? So, solving solving for a, what we end up having here is a equals y bar minus b times x bar, right? So that would be our new one, our new equation 1, okay? Okay. Now let's do something similar with 2, right? Let's try and expand it and then see if we can easily find b from what we know from the new expression that we have for the first equation. Okay? Okay, so this is our second equation. Okay, let's try and do something similar to what we had here. Right? So let's do a little bit of algebra first with that second equation. So we're going to have summation of yi's times xi, right? So let me write it down here. Then we're going to have minus a times xi then we're going to have xi squared. Agreed? Yeah? So now let's try and expand that. Okay? So we're going to have summation of xi's, yi's, right? We're going to have minus a times the summation of xi, right? Then we're going to have b times the summation of xi, because it's minus, right? Minus b times the summation of xi's squared I goes from 1 to n, I goes from 1 to n, right? Agreed? So that's equivalent to the second equation. Make sense? Just doing a little bit of algebra. Now note that we could multiply by an n here, right? And this guy here would be now x bar, right? So let me rewrite that equation like that. Now instead of this, let me just have an x bar. Okay? Okay. Now, remember that from our new equation 1, we had this. So instead of an a, let's plug in. Okay? So now this guy here, the second equation, will be given in terms absolutely of b, and then we should be able to do something about it. Okay? Right? Okay? Just plugging in from what we know from that new equation 1, right? Now let's do a little bit of algebra and see if things simplify a little bit. So what we have is n times y bar, right, minus n times b times x bar squared, right? Right? That's what we have here. Minus n times y bar minus plus minus, well, that should be a plus, nb times x bar squared, right? Okay. So finally, let's place the terms with a b on one side and those without b on the other side. Okay, so let me copy paste this. So let me place these guys on the right hand side. Okay, and here n times x bar y bar, right? B x bar squared. Okay, that looks better. Okay, are we good? Okay, so now let's factor out that b. So if we factor out that b, right, what we're going to have is n times x bar squared, right? Let's see. And then, oh, by the way, right, these guys have to change signs. Since I placed them here, let me modify that, right? Let's just be careful, okay? So here, up to this point, we agree, right? But then what I did is I moved these to the right hand side. So this one, instead of a minus, should be a plus, and this one, instead of a plus, should be a minus. That's better, right? Okay, just to make sure that everything is okay. So what I did here is I plugged in a, right? Then I just did the math. N times x bar y bar, this guy, minus times minus plus n times b x bar squared, right? And then what I said is I'm going to move the terms that have b's to the right hand side. And when I did that and I just copy pasted it, right, I forgot to change the signs of these guys. So this should be a plus, this should be a minus. That's good. Okay, now let's factor out the terms that have a b in it, right? So when we do that, that's what we're going to be doing next. Here what we have is this. Makes sense? B times summation of xi squared, b times this, right? B times negative n x bar squared is equivalent to this. So we're good, right? Now let's solve for b, right? So what we're going to have is this divided by this. Okay, makes sense? Okay, now, so from this, right, what we have is that the solution, right, is a possible solution would be this. First you find b using these formulas, right? Summation of xi yi minus n times x bar y bar, right? Divided by summation of xi squared minus n times x bar squared, right? And in your textbook, right, in our textbook, they refer to this guy, right, as x bar y bar, right? And that's why it's good to make separation here. So in your textbook, they refer to the first term here as x times y, the whole thing bar, x, y, the whole thing bar. That would be that guy. Okay. Oh, for some reason it's not letting me do this. Oh, okay. So let me try and open another one. So in your textbook, right, they refer to this as x bar, x times y bar, okay? X, y, the whole thing bar. Oh, it's not letting me. For some reason, it's not letting me. Okay. Anyway, in your textbook, they refer to summation of xi, yi as x times y bar. And then they refer to this guy as x squared bar. Okay? So you end up with the same formulas, right? If you divide by n here, the numerator and the denominator, right? That's what they refer as to what I was saying. Let me try again to write this down in terms of the solution that they have in your textbook, right? So if you divide by n here and you divide by n here, right, then you will have the expression that in your textbook, this guy here, right, first one is what the authors refer to as x, y bar. Oh, it doesn't let me. Let me see if I can do it like this. X. Okay. Minus just x bar times y bar, okay, which is different, right? It's just, can you see that? That's why I wanted to make that distinction. The authors refer to summation of xi, yi divided by n as x, y time, well, x, y bar, right? And that's different from x bar times y bar, right? That's why I wanted to make that distinction of the notation that the authors in your textbook are using. And then they use to refer to this guy, summation of xi squared divided by n, as x squared bar. We'll see if this allows me to do that. No, it won't, right? Because I want to have a whole bar here, right? But now you see what I mean, right? That let me see if I can do it with another option here. Yeah, maybe with this one. Okay, right? So that's what they have there. Summation of xi squared divided by n, they refer to x squared bar minus minus, and then we have just x bar squared. Okay. Okay. So I just wanted to make sure that you guys understand the notation that they're using in your book, right? Just be careful with that. But it's the same as this, as what we obtained here, right? Okay, so bottom line, let's summarize what we have done thus far, right? And then we're going to talk about an alternative form for the least squares line, okay? So what we did here, right? Let me open a new one. So we said that our prediction, the least squares regression line, the line that we're going to be proposing, has the following form: a plus b times xi, right? And we said that what we wanted to do was finding the best b and the best a, right? And the criterion was to minimize the sum of squares for error, right? So these guys are the least squares estimators, okay? So b, the one that we have to find first, is this guy, right? This is the formula that we came up with, okay? And we know that the authors from your textbook have a particular notation for that solution, right? But I think that it's better to have this one to be more explicit about what the quantities mean, okay? Okay, and then that would be the estimator for the slope, okay? Slope, the estimator for the slope. And the other one, a, right? What we said that a was going to be is y bar minus b times x bar. So first you find b, and once you find b, you get to find this guy here, right? For this particular regression line. Let's call this one the original, because later we're going to talk about an alternative regression line, okay? And this would be the estimator for the true slope for alpha, right? Y-intercept, the estimator for the y-intercept anyway, okay? So, summary of what we wanted to do. Let me see, where do we have it? Okay, so the main thing is this, right? We had a set of n pairs of numbers, x1, y1, x2, y2, up to xn, yn, right? And we had a scatter plot, and we wanted to come up with the line that fits our data best, right? The criterion was minimizing the sum of squares for error, right? And what we did is we minimized that function as a function of a and b, right? So we took partial derivatives, set them equal to 0, and solved the resulting system. So bottom line, these formulas give you the line that fits your data best according to that criterion, and because the criterion is the sum of squares for error, these guys are called the least squares estimators. Make sense? Okay, so next time in another video we're going to show that there are other expressions for the solution of the slope, and we're going to talk about an alternative form for the least squares regression line. Okay? Well, that's it for now. Thank you so much for watching. See you next time. Bye.